Today's theorem we want to discuss concerns some estimates of the Fourier-Haar coefficients of the function f. So let's have the following theorem, which consists of two parts. Part A, assume that f is a continuous function on 0, 1. The estimate for its nth Fourier-Haar coefficient is the following. Here we have 1 over square root of 2n, and then the modulus of the continuity, which is denoted by w, and here the arguments 1 over n f. Let's first prove this part A of the theorem, and let's recall what is the definition for the modulus of continuity. So w delta f is defined as the supremum where 0 is less than or equal to x, less than or equal to x plus h, less than or equal to 1, and h is a positive number which is less than or equal to delta. Delta is taken to be from 0 to 1, and the supremum of f at x plus h minus fx, the supremum of the following difference. Now let's prove the theorem. First, let's recall what we know about the nth Haar function. We know that the nth Haar function is 0 when x is out of the closure of the dyadic interval delta n, and it is 2 raised to power k over 2 if x is in its left half, and it is negative of 2 raised to k over 2 when x is in the right half. But what is delta n? Is the interval from e minus 1 over 2 to k to e over 2 to k, given that n is 2k plus I, where I changes from 1 to 2k. These are some preliminary notations. Now, CNF, what is the definition for CNF? Let's recall. It is integral from 0, 1, ft chi nt dt. So, is equal to 2 raised to k over 2, and then modulus of integral from e minus 1 over 2 to k to I minus 1 to 2 to k plus 1 ft dt minus, this is the bounds for the first integral, are is the left half of the dyadic interval delta n. Now we will have here the right half of the interval, which means from 2i minus 1 over 2 to k plus 1 to I over 2 to k, and the same ft dt. This fact immediately follows from the relation we know about the nth Haar function. So this is easy to see. Next, we will do some substitution. Here, t will be substituted by some u plus 1 over 2 to k plus 1. After that, we will notice that u is t minus 1 over 2 to k plus 1, which means that the lower bound, the smallest value for u, will be when t takes its smallest value, which is 2i minus 1 over 2 to k plus 1, minus this 1 over 2 to k plus 1. And it is obvious that this is I minus 1 over 2 to k. When t takes its value I over 2 to k, after subtracting 1 over 2 to k plus 1, we get exactly to I minus 1 over 2 to k plus 1. Therefore, the meaning for this substitution is to have the bounds of the second summand in this algebraic sum equal to the bounds of the first integral here. So then putting t in the place of u back, we get that this equals 2 k over 2 modulus integral from I minus 1 over 2k, and then the middle point 2I minus 1 over 2 to k plus 1 ft minus ft plus 1 over 2 to k plus 1 and here the dt. Using the triangular inequality, let's have it as 2 to k over 2 integral I minus 1 to 2k to I minus 1 over 2 to k plus 1, and in the modulus ft minus ft plus 1 over 2 to k plus 1. Using the fact that I takes the values from 1 to 2 to k, we notice that the smallest value for this lower bound, I minus 1 over 2 to k, will be 0. And the largest value for this 2I minus 1 over 2 to k plus 1, the upper bound of this integral, will be, if we substitute 2k for I here, we get that here is the largest value is 1 over 1 over 2 to k plus 1. This gives us an idea to use the expression for the w, for the modulus of the continuity of f, and put here 2 to k over 2 integral from I minus 1 over 2 to k, and here to I minus 1 over 2 to k plus 1, and here will be w 1 over 2 to k plus 1, and f here. Then we need some space here, some more space. Let's erase this formulation. Equals 2 to k over 2, and then integral equals 2 to k over 2, and here 1 over 2 to k plus 1. Let's also use the estimate for this w 1 over 2 to k plus 1 f, and put here w 1 over n f. Then we get 1 over 2 raised to k over 2 plus 1. Yes, so this is k plus 2 over 2. And here w1 over nf. Then we will put here equals 1 over square root of 2 to k plus 1 raised to 1 over 2, and then also our omega 1 over nf here. Then, because 2 raised to k plus 1 is greater than equal to n, we can substitute in to k plus 1 and get something larger. So we will put here less than or equal to 1 over square root of 2 times n w 1 over n. So first part of the theorem holds. Now let's go to the second part of this theorem. Theorem B. So f, let's take f to be from LP 0, 1, where 1 is less than or equal to p is less than infinity. Then the estimate will take the following form: less than or equal to n raised to 1 over p minus 1/2 times w p 1 over n, comma f.